Introduction to exponentials and logarithms. Let's start with graphing some exponential functions so we can get a general idea for what these look like. You might have seen a bunch of them on the news with growth of virus cases around the world. Okay, let's start with y equals 2 to the x power. Base 2 would indicate a growth rate that doubles every day. So let's go ahead and plug in some numbers, maybe some negative numbers, some positive numbers. 0 is always a good number to plug in. So when I say plug in, that means I'm taking the numbers that I'm choosing for x and I'm plugging them into my formula and I'm getting out a value for y. So 2 to the negative 1 power is the same thing as the reciprocal of 2, which means it's 1/2 or 0.5. And I accidentally wrote a 5 instead of a 2. Let me fix that. 1/2 or 0.5. And I don't know why suddenly I'm writing in purple, but that's fine. Let's go with it. So then let's do 2 to the 0 power. Just a reminder that anything to the 0 power is 1. And then we have 2 to the first power, which will be 2. And then 2 to the second power, so 2 times 2 is 4. Let's go ahead and sketch these points. So negative 1, 1/2, 0, 1, 1, 2, 2, 4. You can see that the numbers are doubling each time. And so we get this graph here. I don't know if I can draw it very well. With an exponential graph that's growing exponentially, doubling every day. Okay, next let's look at what happens if we do 5 instead, because it changes it slightly. So again, I'm going to throw in my same numbers, but use 5 as the base. So 5 to the negative 1 means 1/5, which is 0.2. 5 to the 0 is 1, because anything to the 0 power is 1. 5 to the 1 is 5, and then 5 squared is 25. We're not even going to be able to fit that number on our graph. All right, so negative 1 is at 1/5, 0 is at 1, 1 is at 5, 1, 2, 3, 4, 5, and I can't fit the other one on my graph. So just here it is. So base 5 means that it would be 5 times as much every day. So, or whatever time period. It doesn't have to be day. Like maybe it's 5 times as much every year, or whatever it is that's growing exponentially. But notice how this one has a steeper shot upwards than the one with the base of 2. So base 2, base 5. Okay, let's look at some fraction bases. For these, I'm going to kind of go the other direction. Let's plug in a negative 2, go a little bit further negative, and go up to 1 instead. You don't have to do that, but I'm just suggesting numbers we can plug in. So negative 1/2 to the negative 2 power, the negative flips it over and squares it. So that's going to take our 1/2 and turn it into a 2 and then square it. So we get 4. You can use a calculator to show you that that's true if you need to. And then 1/2 to the negative 1 power, 1/2, negative 1 power just flips it over. 1/2 to the 0 power is always 1. And then 1/2 to the 1 power just stays 1/2. So graphing this, I get negative 2 up 4, negative 1 up 2, 0, 1, and 1, 1/2. What you see here is a reverse of the first graph we did. So this one would be exponential decay because it's going down instead of up. All right, the last one has a 1/4 base. I'm going to plug in those same numbers again. So 1/4 to the negative 2, flips that over and then squares it. So 16, and then 4. 1/4 to the 0 is 1, and 1/4 to the 1 is 1/4. So at negative 2, we're up at 16. That's too tall. Negative 1, we're up at 4. 0, we're at 1, and 1, we're at 1/4. So didn't hit that line very well, but you can see that it's a decay graph that's a little bit steeper. Exponential decay would include things like the value of a car. I just bought myself a new car, and you might buy a brand new car and it loses value quickly. So quickly, you're going to owe more on it than it's actually worth because they lose more at the beginning and then they kind of flatten out. And honestly, this curve would eventually come back up, not making it a true exponential decay because older cars, they become classics and they become worth more again. Okay, so just quickly, let's observe similarities and differences. None of these graphs that we did have gone down to the negatives. They've all stayed in the positive values because those bases of the exponents were positive. So it's kind of like they're never going to go past 0, are they? They're never going to go negative. So we kind of have like this asymptote here that we're going to talk about at x equals 0 that our graph never crosses. Also, another thing that's the same on all of them is they're all crossing this point at 0, 1. And that's because the power of anything to the 0 power is 1. So you always have that intercept at 0, 1. So that's one thing that's the same. You can make your own observations here, but we have an intercept at 0, 1, and they never go below 0. Stay positive. Okay, so how are they different? Well, we already kind of talked about the differences in these is the larger base is steeper. And same thing here, the larger number in the fraction of our base makes that one a steeper decline. And then the difference between the two graphs themselves, maybe I should switch to this screen so we can see them all at once. So these graphs are going upward and their bases are bigger than 1. And these two, the graphs are going downward with a base that's less than 1. So growth, so these are differences versus decay. So we've got the graphs that are going upward and the graphs that are going downward. Okay, let's put this all together. That was exploration. I'm going to go back to a big screen. So f of x equals b to the x power. That's an exponential function with b greater than 0, so our base is always a positive number. And b is not equal to 1. It makes no sense to have a base that's 1 because 1 to any power just keeps staying 1. F is a one-to-one function, meaning that every x value is connected to a y value that is unique. If b to the m power equals b to the n power, then m equals n. We already saw videos that I created on that use that one-to-one property to solve exponential functions with the same base. The domain from left to right is going to be all real numbers, so I'm just going to list that as negative infinity to infinity. The range is not going to include 0 and not be negative, so it's going to go from 0 to infinity. There's an x-intercept at 0, 1 because anything to the 0 power is 1, and there is no y-intercept. Okay, scratch that and reverse it. I did it backwards. And now I'm moving my whole screen instead of just what I wanted to move. Okay, so the y-intercept is at 0, 1, and there is no x-intercept because there's an asymptote. So we have a horizontal asymptote at y equals, is it y? Yes, it's y. Y equals 0. Okay, and then you can see exponential growth. We've got the base that is bigger than 1. So our base is greater than 1. And then in the second one, this is exponential decay because the base is smaller than 1. Another way they've written it here is just with 2 to the negative x power. Remember how a negative value can cause a reflection? So this is a reflection over the y-axis because of the negative on the x. But another way of listing that is just instead of a base 2, it's a base 1/2. So in that case, our base is less than 1. I keep writing that wrong. Our base is, one of these times I'll get it right, between 0 and 1 for decay. All right, I'm going to stop the video there and start another one.